this video, we're going to consider chill beam water piping options at the zone level. To get started, first thing we want to remember is that chill beams, just like fan coils, come in either 2-pipe or 4-pipe. So here's a picture of a 4-pipe chill beam. You can see the blue connections are marking out the chilled water loop, and the red connections are marking the hot water loop. So this coil slab has 2 separate water circuits in here. About 2/3 of the tubes are dedicated to cooling and about 1/3 to heating. And so also want to point out that these are just straight copper connections, so they could be you could braze to these things, although you have to be incredibly careful not to cause any heat damage, especially to the finished surfaces. More likely you'd have some kind of push-on or compression fitting that would hook onto these coil connections. Now this is a 2-pipe chilled beam, and you can see we're down to 1 set of connections. And in this case, 1/2-inch MPT threaded fittings have been added to the coil. You can see all kinds of connections on chilled beams, and it'll just depend on the manufacturer and what the engineer wants to specify. Now before we get too far into the piping options, I think it might help you if you just get a chance to see what chill beams look like. So I'm going to show a bunch of different pictures of construction projects, and just so you get a sense of what it's going to be like, not just be looking at a set of plans, but to actually see a building under construction. So you can see here the beams have been hung from the ceiling. In this case, the contractor is using threaded rod. And right now he would have these beams hung a couple of inches above where the suspended ceiling would go in. Notice these have been put in before the ceiling. And then once the ceiling goes in, they would be lowered down into the grid. So these things are threaded rods adjustable to lower the beams down. And then after that, also to, of course, be roughing in the piping and the primary air ducting. Now here's some examples of open ceiling concept chill beam applications. So this is a finished chilled beam. This is a Swagon Adriatic beam. The conditioned air comes out through these slots on the side. The return air comes in through the grill on the bottom. And this has been left in an open ceiling concept. And you can see that this is a 2-pipe system. And you can see that here's the water lines coming over, and then they're using flex connections. You can even see the ball valves for isolating this. Over in this picture, you're seeing a slightly different style. This is a kind of a pendant style of chilled beam. They've had what they call Quanda wings added to it. The air comes out through the slot. Quanda wing helps with the air distribution. And in this particular project, these face plates run the entire width of the building, even though the entire chill beams are not active. So this is a visual faceplate for continuity. It lines up well with the clouds with the light fixtures in them. But some of these beams are active, and some of these panels are just for show. But again, you can see the water lines coming over and connect on the top, and all hidden above the beam. Now here's some applications. These are actually 2 different projects where we have 4-pipe chill beams, and they're in a ceiling grid. And one of the claims of a chill beam system is it needs a very small ceiling plenum because the beams are so small and the ductwork's small, but that doesn't mean it isn't crowded. So look how close the ceiling grid is to these pipes passing underneath the structural steel member here, and you can get an appreciation of how tight this is all going to be, which you can see the piping's been insulated and run over. The beam has been lowered down into the ceiling grid. Of course, there's the primary air. It's all been hooked up. Here's another example of a chilled beam at the top of the picture. And again, you can see the water lines coming over. There's more ceiling plenum space in this, but it's still pretty tight when you're passing underneath the ductwork to get the beams all over. And remember that chill beams are dry devices, so there is no condensate pan, there's no condensate piping to these things, so it's just 2-pipe or 4-pipe water supply to the beams. Now here's a chill beam that's been drywalled into a ceiling, and they can come with what we call a plaster flange for all different kinds of beams. But immediately you're going to need a service access section over here to allow you to get up to service the valves and be able to shut off the isolation valves to this beam if you ever needed to service it or do anything as well. So something you have to consider in the layout is that these beams need to be located someplace where you can service the valves. Now, this is a what you might call a bulkhead or a horizontal chill beam. This is actually what it will look like when it's all furred in with the drywall. The return air comes in through the bottom. It jets out through the front grill, which you can see right here. You can see the bottom return. And up here, if you have a look, you can see the contractor has roughed in the water connections. They're capped off so they can do the pressure testing, and after all the testing's been signed off, they can cut these things off and do the final connections. You're going to want to isolate the chill beams for the flushing process, and do the connections in here. And of course, as the drywall goes in, this will get harder and harder to work around. Beams also can be mounted across the wall. Often when you do that, the lines are dropped down through a corner furring or brought up through the floor slab to these units. Often the enclosure lines up with the window mullions, whatever the style is. And one of the ways you can pass across multiple chill beams around the perimeter is to have the chill beams supplied with a piping rack like you see here. You can see this is a 4-pipe system. And the water was drawn off of these things so that it could pass on to multiple chill beams on the same facade of the building. This is an underfloor application in here, so you've got the lines on the floor. You can see they've been insulated in here. We've got shut-off valves and then flex hoses over to the coil. This is a 4-pipe coil, and the air is underneath the ceiling or underneath the floor. Drawn through this coil. This is the primary air. The nozzle bank is actually right along there and creates a low pressure area underneath the coil that draws the air that's coming from the room into the floor plenum, and then is delivered back through this slot here, back up through some form of slot diffuser in the raised floor. So that's an idea of what beams are going to look like when you see them in the space. Let's start to talk about how they get piped up. So over here we have a 2-pipe beam application. Pretty common thing to see. You've got copper lines coming in, and then very common to see flex hoses used. This allows for adjustment as the beams are threaded rods are used to lower the beams into the ceiling grids. You can have that flex connection if you need to move the beams around a little bit. And so a lot of projects have fire rated or stainless steel braided hoses connected to the units. And it's also very common to see some form of isolation, a ball valve or something, so that if this beam needs to be serviced or has any issues, you can isolate it from the main loop. A little bit about hoses and their connections. You can get them in all sorts of shapes and sizes. They're usually between 1/2 and 3/4 of an inch based on the flow rate required in the chill beam. Chill beam flow rates are quite low. They're usually between 1 and 2 GPM. And you can get them in different lengths from whatever you want, but typical lengths are in the 18 to 24 inches if you're in a ceiling plenum, and then 12 inches if you're doing something that's tight and there isn't a lot of space for excess hose. In terms of the connections, these are push-on fittings. They could be John Guest style or shark bite or whatever the manufacturer is at one end. And then at the other end, you could have a threaded connection that could be used with a coupling onto a beam that has a brazed threaded connection, an MPT connection. Or you could have this, which is a compression fitting that would go straight on the copper and could be tightened up and would pinch down on the copper with the compression fitting. They're all available. You also see, we talked about flexible hoses. It's on some projects you'll see hard connections. So you can see this chill beam is actually an exposed style chill beam. It's in a finished cabinet. It's not going to be moving. And in this case, the consulting engineer called out that they be hard piped. It's one less thing that could go wrong. A hose wouldn't necessarily describe it as a weak point, but it is one more thing in a water-based system that could give you trouble. And so you can see that they are hard piped. Some things about accessories that you often see associated with chill beams. So an air vent, not a bad idea. So you can have a unit in here that would allow you to bleed the air out. It's always a good idea to have some form of isolation valve. Nice thing to do is to get one with a drain plug in it. You can potentially order the beams or with a drain plug in them but it's often done in the piping and the hoses, so you can drain whatever water's between the two valves and whatever in the coil. And when you break the hose connection, you'll be able to catch that water in a bucket if you ever needed to drain down a coil for some service reason. You will on occasion see a circuit setter balancing valves being used. It's nice to have the taps, but remember these flow rates are down around 1 GPM. This is a fairly expensive device. It's a really nice thing to have, but it could run the cost of the project up, and so I wouldn't casually go out and apply them, but certainly wouldn't say it's a bad idea if you're going to do that. Strainers possibly in the systems. These are small coils, not something you want to have fouled, but again, this is going to be in the occupied space. If it's near the beam, this is one more thing that can leak, and it's also in a tough place to do any kind of maintenance on to clean that screen out. And here's a picture of an assembly that would fit onto the coil. It's actually got a control valve built into it. They could be on, off, or modulating. Some of the control valves use what they call a hot wax. It's very popular in Europe. There's actually a little heating element in here and a wax in the actuator. As the heat warms up, the wax expands and it pushes the plunger down, opens the valve, and then when the space is satisfied, the 24 volts to the actuator is that circuit's broken, and the wax cools down, and over a few minutes that valve slowly closes. And it slows the valve actuation down so that you're not opening in 10 seconds or 20 seconds, running for a few minutes, and then closing. You're taking 2 or 3 minutes to go through a cycle, and it just helps smooth out the condition. So a very popular thing to see done in Europe, a little less so in North America. And you see it all comes in an assembly. Now we'll talk a lot about whether or not you should have valve control at the specific chill beam, or should you use zone control. And it really depends on your building type. If you're doing a hospitality, a hotel room, then every hotel room is a control zone, and having the valves mounted on the chill beams is advantageous for you. If you're doing general office space or classrooms or whatever, then we would treat them as normal control zones. You're almost certainly going to have multiple chill beams in that, and we would say one valve per control zone. Then you wouldn't mount it on the beams themselves, but you would mount it on the piping that services that control zone. And we talk a little bit about what kind of piping systems do you see, what material is used. Copper would certainly be the most common. You can see that in this project in here, where they're starting to rough in the piping over close to the chill beams here, and the ductwork starting to come in. Connections are on. Normal to see chill beams supplied with protection during assembly to protect the finished surfaces, and having little plastic bags over the air inlets so we don't fill them up with construction dust. It's a nice touch. This is actually a passive chill beam application here. So you've got piping coming in here, and where you can add water to these things. And again, you can see the flexible hoses and the ball valves to isolate it. Here is a different application. This is a exposed beam, but notice that they're actually running steel or black iron pipe here, and then hard connecting in here. This is less common, but certainly possible to do. It really depends on the engineer's preference for materials, and also what the best construction price cost is for you in your territory in terms of what the contractor can run. And you hear a lot of talk about using PEX in chilled beams. It shows up in a lot of presentations, a lot of discussions in here. In the grand scheme, we don't see a lot of it being used yet. I think a lot of that has to do with local codes and acceptance in open plenums around fire codes and what have you. But as this material becomes more popular, this is a very cost-effective way to do it. It would really depend on your local codes and the engineer's comfort level with using this material. There's certainly no issue from the chill beams point of view to use this kind of material. Well, let's talk about the piping and the controls in here. And we're going to first talk about two-pipe chill beam applications. So we're going to have a control zone in here. We're going to have 4 beams in this control zone. There's going to be one controller for this control zone that's monitoring the temperature in the space and has some way of keeping an eye on the humidity or the dew point in the space. And being a two-pipe system, we have a chilled water supply and return lines running around the building. And we're going to treat this as one control zone. So whatever happens to one beam, we're going to do to all of them. There's going to be one chilled water valve here that's run by this controller, and if the temperature climbs, we'll see that that valve will start to modulate to do that. Now the way we've drawn this piping in here is direct return. Reverse return is fine. It really is going to depend on how the beams are laid out and how you can run it. Nice thing about reverse return piping is it means that all the flows will be balanced and that the system will self-balance and deliver the same amount of flow to all these beams. In a small system, direct return shouldn't make a big difference. In a larger area, probably would recommend that you look at reverse return piping. Once this valve opens, and if it was 1 GPM per beam, and this valve opened to 4 GPM, you'd kind of want to make sure that roughly each one of these beams sees 1 GPM, and reverse return piping will help you do that. Now this can only do cooling because it's a 2-pipe system. In theory, you could do a 2-pipe changeover and at some point switch from chilled water to hot water. Seems like a very rare application in chilled beams to do that. More likely this would be what you would see in the core of a building where we're only going to see cooling load, or you're going to see it everywhere, but if this was the exterior exposure, there would be hot water, some kind of radiant or wall fin along the wall, and so the heating system would be separated away from the not done by the chill beams, but done by another hydronic system or electric system to do that. Well, let's see what happens when we go into cooling mode. Now we see that we've moved off of our deadband. We've seen a shift. You get some cooling from the air, as we discussed when we talk about control sequences for chill beams. This is now the controller sees demand, and it responds by starting to modulate the chilled water valve and allowing flow through the beams, and so we get additional cooling to meet that load. Now, something you can see in a 2-pipe system would be to do this, is to put some form of reheat coil in the primary air. Normally this air coming in is typically 55 degrees. That's not a requirement. You might even talk about resetting that air temperature in the winter. But if you had a zone where you might want to be able to add some heat to it, but you didn't want to buy 4-pipe coils and do all that additional piping out to each one of the beams, you could put a coil in the primary air, tap it into your hot water loop, and now you have the opportunity, the controller, if it sees the temperature drop, as we see here, we've moved below the deadband, it can modulate that valve to put heat in. Do remember that only about 1/3 of all the air that's moving through this room is the primary air. The other 2/3 is the room air that's passing through these coil, and you're only putting the heat into this primary air. So there's a limit to how many BTUs you could actually introduce into here without getting some fairly high air temperatures in this primary air, and how well the beams would work, and possible issues of stratification. You'll get the heat into this control zone, but you might find that the air doesn't distribute as well as you want. But for a little bit of reheat, this is a very viable solution. Well, let's talk about 4-pipe chilled beam system in here. Now we've got both a chilled water loop and a hot water loop distributed throughout the building. And in here, the system is neutral. The temperature is being met, so we have no heating and no cooling. So both the hot water and the chilled water valves are closed. And we're just providing, you're getting a little bit of cooling from this primary air, this 55-degree air that's going into the space. So there's a little bit of cooling going on. And so the controller can use these 2 valves to modulate it. And again, we're showing, kind of direct return piping through here, but reverse return piping would be fine. And as this zone gets bigger and you have more and more beams in it, reverse return piping would actually be advantageous just to keep the flow rates balanced. Let's have the situation where we see a cooling load in the space. So you can see the room has moved out of the deadband up into here, and so we're going to start to modulate chilled water through the beams to help getting some cooling effect. And so the hot water valve will stay closed, and the controller for that zone will modulate this chilled water valve, allow some water into these beams to meet the cooling load as necessary. The reverse will be true if the beam goes the other way and the zone temperature drops and we need to add heat. what would happen here is that the chilled water valve first would be closed, and if the temperature continued to drop, then we would start to modulate the hot water valve. And the first thing the heat that's going in these coils is going to do is to warm this 55-degree air up to 75 degrees. It's actually providing a cooling effect all the time. We have to negate that first. And then if the space temperature continues to drop because there's heat loss through an exterior exposure or something, then what we would do is continue to add more hot water to it. This supply air temperature would start to go up above the room temperature, typically not more than about 10 degrees Celsius or 15 degrees Fahrenheit. Otherwise, we start to get buoyancy issues and stratification issues. But we can add that heat into the space and meet the load. Now, something else you're seeing a lot being used in chill beams these days are six-way valves. So if you're not familiar with them, let me introduce them to you. This is what they look like. This is a valve that Swagon offers. It's actually a small valve. It's sized to be actually mounted right on the chilled beam. Where we use this is on what we would call our bulkhead or our Paragon product. And that product is used in hospital patient rooms or hotel rooms or kind of single bedroom type applications. And there's which means it's one chilled beam, one control zone. So you are going to have a valve that does that. Nice thing about doing this in like a hotel room application is that actually in a more temperate climate, heating can be one of the more dominant loads. And when you use a six-way valve, you can get a lot of heating capacity out of it, which I'll show you here in a second. So this is a valve from, I'm sure you'll recognize the Belimo. It's a larger one, so if you're doing a larger control zone and you had 5, 6, 10 GPM of flow going through it, this valve is more than capable of doing that. So how do these work? Well, the reason they're called six pipe is there's 6 connections to them. So right now you can see where the building loop chilled water connections are right here. The other 2 pipes that are grayed out are actually the hot water connections, and this beam is in cooling mode. So what it's allowing is it's drawing water off of the main loop, allowing that to go through the coil. All the coils for all the chilled beams that are on this would be 2-pipe chilled beams. Even though you're going to be able to heat and cool with them, every tube in that chilled beam is going to be used in one water circuit, and when you looked at the beam, there'll only be one set of connections on it. And that improves the capacity of the beam because you're not splitting the coil 1/3 heating, 2/3 cooling. It helps you a bit in cooling, gives you a little bit more capacity. It makes a significant increase in the capacity of the beam in heating because you got a lot more tubes that can add heat, which is why it's really popular in hotels and in dormitories and single room applications where you're going to use chill beams in a residential application. So we can see this in cooling. Let's just switch over. Now you see it in heating. The valve has moved its position and has connected the coil to the hot water loop that's in the building. And so now you can see that the hot water will flow out through the coil. You got every tube in that coil is adding heat, so you get a lot more capacity. So it's a good thing to point out here is that when you switch from one system to the other, you are definitely going to flush water from one system to the other. Not a lot, but you will do it. So both loops have to be, for instance, straight water. If you had a situation where your chilled water loop had some glycol in it because the chillers were outdoor and you wanted to protect it, this would not be a good application. You would end up flushing the glycol slowly but surely out of the chilled water loop and into the heating loop. So it's always a good requirement that you have straight water in both systems. A little bit more detail about how the valves work themselves. Imagine you have a control valve that's modulating with a 0 to 10 volt signal, so you can get a sense of what's going to go on here. That between 2 and 4.1 volts, you're going to get the cooling performance in here, and so that's this part here. So as the voltage signal goes up, this unit will increase the amount of chilled water flow. And if that's not enough, then I'm saying that backwards actually. We're going to go from low flow or high flow to low flow. Then we're going to reach the neutral, where neither circuit is open to the coil, so that you're in the dead band. And then if the voltage gets between, say, 7.2 and 10 volts, you're going to see that you start to modulate the heat on. And so for the unit controller, the zone controller, they just send one 0 to 10 volt signal out to this valve, and then it will modulate the two different loops. Another thing about these valves is they typically have adjustable CVs, because you're going to have a different CV in heating and cooling, and so you may need to be able to adjust that to get good valve authority. We mentioned the part about don't mix them with glycol. And somehow you usually need to have some way of relieving the pressure. If you have a six-way valve that's servicing let's imagine a classroom, right, which would typically have 4 to 6 chill beams in the ceiling. There's a reasonable amount of water in the piping and in the coils. Once you close off one of these loops, if you go from cooling to heating, there's no expansion tank on that cooling loop. So as that water warms up, as it sits idle in the pipe, it's going to expand and put pressure on it. And so internally to the valve, you want to be able to bleed that pressure off and not have any issues with the expansion, cracking a joint in the piping system. So that's all looked after inside these valves. So let's look at how one would be piped in. And we said it would be a 4-pipe system. So you've got a hot water and a chilled water loop. Here's the 6-way valve. Right now we're neutral, so we'd be at kind of like 5 volts on that control sequence. So the valve would be sitting in the middle, not allowing either hot water or chilled water to get out to the beams. And here's why you can see why they're so popular. If you have that image of a classroom in your mind, and you think about a space that's 1,000 square feet with 6 beams in them, there's a fair amount of piping going on in that room up above the ceiling. There's a lot of joints. There's a lot of labor in here. You're going to cut that labor and material in half within the classroom to get it back over to the valve. And in addition to that, you get the increased capacity from the beams, because every tube in the beam can be in heating, or every tube in that beam can be in cooling. And so you just get more capacity from the beams. So nice solution when you can do it, and it helps with managing your capital budget. So right now the system is neutral. So let's shift it into a cooling load. And so the heat load is raised in the space, and the way the valve responds is that the controller sees that through the temperature sensor, and it modulates the valve into its cooling mode and allows chilled water to flow out to all the beams to meet the cooling load. Now, we go back the other way and we switch over. We close off the loop to the chilled water. Remember that when that happened, all that piping had been filled with chilled water. The coils were filled with chilled water. And so when we switched over, all of that flushed out and went back into the heating system. So you are going to move water from one loop to the other. That's just part of a six-way design. But once that's done, we're going to allow hot water to come in here and warm this air up and meet the heating load in the space, and so we can modulate that. So that's a quick tour of what goes on at the zone level on the hydronic side, and a little bit of detail of what these mechanical rooms look like. And hope you enjoyed it. Thank you very much.